Good morning, everyone. My name is Shazain Aslam. Today, I am pleased to present my presentation titled "A Machine Learning Framework for Diabetes Risk Stratification and Complication Prediction" at International Conference on AI Innovation and Industry 2026. This research focuses on building an explainable and integrated system that moves beyond simple prediction toward early risk awareness and proactive healthcare decision making. The aim is not just to detect diabetes, but to understand patient risk level and support more informed clinical decisions. Uh, in our presentation today, we will cover, first of all, we discuss the problem of diabetes risk prediction and the challenges in healthcare. Then I will explain our proposed framework, including both the data processing and modeling stage. After that, I will cover the supervised learning algorithm used along with techniques for handling class imbalance. I will also describe the benchmark clinician dataset used for evaluation. Following this, I will explain the unsupervised risk stratification approach. Next, I move to the problem formulation. To begin with, diabetes is a growing global health challenge with increasing rate of complications and hospitalizations. This highlights the urgent need for early and proactive intervention. However, healthcare data is highly complex as patient high dimensionally. In addition, many existing AI systems operate as black boxes, which limit clinical trust and adoption. Therefore, the key problem we address is how to build a system that not only predicts risk accurately, but also provide interpretation insight that can support real-world clinical decision making. Next, we discuss about the pipeline stage one data processing. Our framework begins with the data processing stage. We start with raw hospital data, which often contain missing and inconsistent values. So we apply missing values imputation techniques to ensure data completeness. We then perform feature selection and feature engineering to identify the most relevant clinical variables for prediction. Finally, we applied dimensionally reduction using principal component analysis or PCA, which helps reduce complexity while preserving important pattern in the data. This stage ensures that the dataset is clean, structured, and ready for modeling. Here is the pipeline stage 2 for the modeling stage. After preparing the data, we move to the second stage of framework, which is modeling. This stage integrates multiple components into a unified pipeline. We begin with unsupervised patient risk clustering to understand different patient groups. Then we apply data resampling techniques to address class imbalance, which is a common issue in healthcare dataset. After balancing the data, we trained supervised ensemble models to capture complex relationship. Finally, the system generate complication risk prediction, enabling early identification of high-risk patient. Overall, this stage combines clustering, balance, and prediction into a single integrated framework. Supervised learning algorithm. In this stage, we evaluated three supervised learning algorithms. The first one is the random forest is used as a strong and reliable baseline model. The second one is the XGBoost is particularly effective in capturing pattern in minority classes, making it useful for detecting high-risk cases. The third one is the LightGBM, achieve the best overall performance as it balances accuracy, computational efficiency, and generalization. This makes it high suitable for real-world healthcare application where both performance and scalability are very important. Next, we discuss about the class imbalance mitigation in our dataset. One of the major challenges in healthcare data is class imbalance, where high risk of complication cases are underrepresented. This can negatively affect model performance. To address this issue, we applied three resampling techniques, including the first one is a smooth, the second one is a smooth AEN, and the third one is addition. Among these, smooth produced the best result by generating synthetic samples for minority classes. This significantly improved the model's ability to detect high-risk patients and ensured more balanced predictions. Here's a benchmark clinical dataset that we use in our research. For evaluation, we used a benchmark clinical dataset that contains over 1 lakh patient records and approximately 50 clinical features. The data was collected from US hospitals and widely used in healthcare machine learning research. This provides a strong and reliable foundation for evaluating the performance and generalizability of our proposed framework. Unsupervised risk stratification. One of the key contributions of our work is risk stratification using unsupervised learning. We apply K-means clustering to divide patients into 4 groups: low risk, moderate risk, high risk, and very high risk. Using PCA, we were able to visualize these groups clearly, showing meaningful separation between the patient categories. This step is important because it allows us to move beyond binary prediction and instead understand patient risk level in a structured and clinically meaningful way. Next, I will discuss about the predictive model performance. In terms of model performance, light GBM achieved the highest accuracy of approximately 89.4%. It also maintained a strong balance across different evaluation metrics. This indicates that the model is both accurate and reliable, which is essential in healthcare application where decisions can directly impact patient outcomes. Next, I will discuss about the performance stage of this slide highlight an important concept, which is the trade-off between precision and recall. Precision focuses on reducing false positive, while recall focuses on identifying all high-level risk cases. We observed that the XGBoost performed well in recall, where large GBM provide a better balance between this precision and recall in clinical setting. Missing a high risk patient can have serious consequences, so model selection should be guided by clinical priorities rather than just technical performance metrics. Here's our conclusion for our research. To conclude, we propose an integrated machine learning framework that combines unsupervised risk stratification with supervised prediction. This approach enables proactive clinical action, improves patient risk understanding, and support more informed decision making. Most importantly, it represents a shift from reactive treatment towards a proactive and preventive healthcare system. Next is discussion and some limitation. Like in research, there are some limitation to work. The model was evaluated on hospital US data, which may limit it generalizability to other healthcare systems like the NHS. In addition, the framework doesn't currently include advanced temporal model techniques. Future work will focus on validating the model using more recent data set and improving its applicability in real-world healthcare settings. Thank you for your time and attention. This research also contributed to real-world systems such as sugar care, where predictive and explainable AI is used to support everyday database management. I would be happy to take any questions.
Okay, thank you, Dr. Islam. Any questions from the audience, Shubham? عندك أسئلة? عندك سؤال؟ في بونص. Alright. عندك سؤال دكتور؟ Okay, that's an interesting work and using also 130 US hospitals is a very famous data set that we all use. And it's good. It's a good take on it. For predicting the complication prediction. Can you go to the slide that has the clustering?